So, good morning. Thanks for all coming. My name is John Gossman, and I work in the Azure core team. So, Azure is a Microsoft global cloud system, and the Azure core team, we basically write the software that runs the data centers. So this involves everything from, we have people who write firmware for NICs. We actually do some hardware design now, up to the next level of the basic fabrics for running under the cloud, the compute, network, and storage fabrics, and all the stuff that goes in behind the scenes before you get to any of the public APIs, up to the kind of the first level of the public APIs for Azure, the control plane and basic data public APIs, REST APIs. And so I like to say that then the Azure core team is at the bottom of the stack, and then other teams build things on top of that. So the machine learning team is built by a team in the data group. The SQL service for Azure is built by, again, the SQL group, et cetera, et cetera, et cetera. And so we're kind of, like I said, the bottom of the stack. And my specialty is developer experience and APIs and other things like that. So I really work at the top of the bottom. And the last couple of years, my focus has really been on enabling non-Microsoft stuff to work on top of Azure. Because every customer in the world now has got a mix of stuff. There is no company that you can go to, including Microsoft, that's an all Windows or all .NET shop or an all Java, all Red Hat shop. Basically, everybody in the larger companies has got a whole set of different technologies that they work with. And even startups, this polyglot development, people are picking the tool, the right thing. And if you want to run a service like a cloud, you have to provide a service that actually satisfies those needs. And so I've been spending a lot of time working on Linux, on open source configuration managers like Chef and Puppet, the stuff from HashiCorp. And about 3 years ago, I started really working with Docker on containers. And so this is based on my experience and my peers at Microsoft and my peers at other companies, people in the community, about what containers, where they're coming from, and where we're going. And I usually try and be a little more interactive. Because they're recording this, asked to keep the questions to the end. But I would like to get a bit of a show of hands so I can kind of get a level set for the audience. So my first question is, how many people here are using Docker? Okay, almost everybody. How many people are using Docker in production? Okay. How many of you are Azure customers? Or use Azure? All right, almost no one. That's fine. How many of you came to the talk because Scott Hanselman really gave talk this morning, you thought you'd give the other Microsoft guy a chance? Okay. Leave now. This can only end in tears. In fact, when I submitted my abstract for this talk, the organizers sent back, I'm a developer, and I wrote an abstract that I thought sounded like a marketing abstract, and they sent it back and they said, this sounds like a marketing abstract. And we've had a lot of evangelists who come in and kind of give these professional, very polished, entertaining speeches, but it doesn't really set with the audience. And I'm like, that isn't me at all. I have never given a polished, professional, entertaining talk. So anyway, this talk is on trends, and I just want to say we're living in a time of technological change that is absolutely awe-inspiring. I've been in the business for a long time, so I remember the PC revolution, and I remember the internet revolution, and I remember the smartphone revolution, and these times in the industry which seem to happen about every 10 years, where everything suddenly goes up in the air and everything's changing really fast. It's like dog years versus normal years. We're in this place where the 3 years I've been working on containers feels a lot more like 21 years. So in those periods of time, it's really hard to predict the future. But I can look at the history and look at stuff that's coming and kind of make some guesses. And then it may turn out that there'll be another disruption that'll come along and it'll be wrong. That's what you do now when you're wrong. When you try and predict something, you build a business model or something like that and it fails. is you say, well, I wasn't wrong, I was disrupted. So, but nonetheless, we're in the case where the disruption is right around the corner. So let's go back into the distant past and talk about why containers. And I say the point really is that there's this concept of virtualization. And the concept is really simple. There was a time when you wrote a program and you wrote assembly, maybe you toggled dip switches on the program, and that program owned the entire machine and every single instruction you coded for. That was a long time ago. But that programming model is much simpler. If you try to, if you try and write a program now and you want to run it somewhere, obviously we create all these abstractions to make it look like you own the whole system. Processes are like this. In a process, you have virtual memory. It looks like you have all the memory on the box. You have a copy of the stack. You have some threads and things like that, and you think that you're there, and the operating system does all the work to make sure that the memory is shared properly and processors shared, things like that. But it gives you that level of abstraction. But that hasn't turned out to be enough, because it turns out programs tend to have dependencies, and they work on a particular operating system or kernel or something like that. So people have built other sorts of containers around these things to give you the illusion. You should split up the hardware. And a lot of these things go back a long, long ways. Now, until quite recently, probably the prevalent dominant paradigm was virtual machines with VMware and other hypervisors in the data center, where you're trying to increase the density on your hardware, but each computer could be running different operating systems and different versions and things like that. But there was also all along in these operating systems these lighter weight concepts of breaking the system up. Hypervisors create an abstraction at the hardware level. They emulate the hardware and make it look, you're writing assembly language instructions, you can do I/O, and it looks like you're talking to a real machine, but actually you're going through a software layer. And that means each virtual machine has its own copy of the kernel, because there really isn't anything else. It's all the software in the box is being running on top of this hardware emulation layer. And so containers, primarily the model is that they all share one copy of the kernel. And this has huge performance advantages, because if you don't have to boot a kernel for every application or every system you want to run, it comes up faster, it uses less memory, and yet inside a container, you, again, think like you have the whole machine. You have a whole set of processes, you have a regular process tree, you have your own copy of network mounts and drive mounts, and your own file system, and you can bring along your own dependencies. So if you're writing a Node app and you have a bunch of Node modules and you have the Node engine, you can put it into a container and you can bring it along, and you have everything's isolated and it looks like you've got a whole operating system. And then right next to it, you might have somebody else who's running a different version of Node, or they're running .NET or Java or something else. And these things are isolated from each other. But unlike in a virtual machine where they share a kernel, so it's really just a set of dials. And that's really kind of the point of this talk, is that there's lots of different ways of putting these things together. The point about, hypervisors were this mainstream thing. They were kind of mainstream primarily by VMware and Microsoft and KVM and other people doing things like this. Meanwhile, this container thing was something that real operating system nerds and distributed system nerds knew how to do. It required a lot of complex kernel calls and actually even sometimes work in the kernels in order to make it work, to make these things differentiated. And so you'll hear almost anybody in the industry who comes from that sort of a distributed systems or operating system background talk about, oh, well, we had containers before Docker. But that kind of misses the point. We had containers before we had Docker, but almost nobody could use them. And what Solomon Hykes at Docker came up with is he was building a distributed system, right? He was building a service for distributed systems. And he came up with a really simple set of APIs and experiences that create this really nice developer experience for using containers, and now everybody's using them. And that doesn't diminish that the fact that containers existed before Docker doesn't diminish that at all. In fact, I would argue that the industry is more often disrupted by these kind of aesthetic, ease of use sorts of innovations than somebody figuring out, oh, we can do this interesting new tweak to the hardware and make things faster, or bounce up in the air or something like that. And so, whereas previously container-driven thing was driven really by operational needs, by the increased efficiency and density that you could get. You can pack more containers onto a piece of hardware than you could pack virtual machines onto a piece of hardware. Since the Docker revolution, it's really been a developer-driven thing. Developers just love this experience. If you've ever run Docker, if you've ever done the original Docker run Redis, and like 2 seconds later you've got a running Redis machine, you're like, I will now crawl over ground glass so that every single thing I try and deploy from now on works that way. And the great thing is meanwhile, the CFO and the ops guys know that at the biggest scale, the really big cloud vendors and things have been using containers for a long time to increase density. So it's like one of those fad diets. You read in the magazine, it says, all you do is eat chocolate and drink red wine, and you will lose weight. And so why would you do anything else at that point? Even if it doesn't turn out that you'd actually lose weight in the end, it's going to be a lot of fun trying. So the other thing I would say about Docker is really a huge amount of the point of it is the portability. Virtual machines have never been there have been efforts to standardize virtual machines, but none of them really took off. Whereas Docker, not necessarily because it was standardized, but because one company built the thing and it kind of took off and everybody adopted the same set of APIs, is this really easy way to transfer all sorts of things around. So it's really kind of the new universal package manager. But it's better than if somebody came up with a new universal package manager. Because every other time that somebody has come up with a package manager, it generally turns out that that means you have to get rid of your old package manager and create new types of packages. What this does instead, with Docker, it subsumes all the existing package managers. If you know how you create a Docker file, oftentimes say you're doing something on Ubuntu, the Docker file starts out with apt-get such and such, some packages, and that brings down through the normal apt package manager the dependencies, puts them into that Docker container, and then kind of freezes it in that mode. An NPM, whether it's a language or operating system package manager or whatever. So you haven't had to change anything. You've just got this extra package manager around your package managers that keeps everything around, and then you can just pass the thing around to people. Once they got the Docker file, it pretty much runs. And one of the big advantages of this is that it allows you to test locally and then upload it into the cloud or into your data center. And because all the dependencies are with it, some people call it like it's a teleporter into the cloud, where your laptop and your cloud are much closer together, which is a huge deal. The other thing, if you're familiar with Docker at all, is that they have a concept of a registry. So once you create your Docker image, you push it up into the registry, and then you can pull it from machines all over the place. They also have something called the hub, which is more like a classic universal package manager where you can push public images and then people can pull them. So this is really nice setup. It's really set up easily to work in a CI/CD system where you build somewhere, you launch a build, it goes into the registry, and then you've got the latest version in the registry, and then you can pull things to production. And it works pretty much anywhere. So Docker, when it first came out, it allows you to create a single container, put your code in there, and move it somewhere. But what if you have lots of containers? And you're trying to spread them across the data center in the way, say, like if you're familiar with how Twitter went from monolith to breaking up their monolith into a whole bunch of microservices and spreading it across their data center, or Netflix or any of the other big cloud properties have tried to do this sort of thing. So these all involve something called container orchestrators. And 3 years ago, at the time of the first DockerCon, there were literally like 17 container orchestrators that were announced all simultaneously. Everybody wanted to get into that space. The world has more or less coalesced on 3 of them: Kubernetes, Mesos, and Swarm. Mesos was built at Twitter to solve their fail whale problem, but it actually predates Docker. It's also the thing that Spark originally ran on, and a lot of other things that don't use Docker containers. So Mesos is more general than a container orchestrator. The other 2, Kubernetes and Swarm, were actually built after Docker came out, and they were built with Docker in mind, so that they have a more native Docker integration. Though Mesos, because of its generality, they have a thing called Marathon that is a Docker-oriented orchestrator. And all 3 of these things are kind of finding their niches. Swarm was developed by Docker Inc., and it uses very much Docker APIs. And in fact, if you get the Docker engine, you've now got Swarm mode, and you can just bring up a cluster. And then Kubernetes was built at Google. But this orchestration stuff went from 3 years ago, 17 of these things. There was all these arguments, this one better than this, and we add this feature, things like that. I've hardly ever seen a technology go from just like cutting edge innovation battleground to commodity in it was like an hour and a half. It was like at the end of the conference that they were all similar. There's certainly advantages and disadvantages depending on your action, but it's kind of like programming languages. Do you really want to have another argument about whether Ruby or Python or, well, we won't talk about PHP because Scott already covered that. So the next thing is really the next merging thing is day 2 operational issues, not just orchestration, but how you're going to keep these things running, how are you going to recover, how are you going to monitor it, how do you make sure that the cluster is secure, and then how do you define really applications that are running on top of these orchestrators. By the way, the Azure point of view on all of these things is that we support whatever the customer wants, just like we support Linux and Windows, Java and .NET and Python and all stuff like that. We have an Azure Container Service, but it isn't something that's specific to Azure. It uses the open source versions of Swarm, DCOS, which is a kind of a thing that sits above Mesos, and Kubernetes, and just operates them as a service, so you get to bring in a choice. If you're familiar with RDS on AWS, where basically they operate the database, but it could be your choice of database. It's kind of a similar model. Now, there are still a bunch of things that are emerging in this space. Container networking, when it first came out in Docker, was very simple. There was NATing and port mapping and all sorts of difficult things. And then every data center, oftentimes portability in the cloud is great. It turns out that everybody's networking stack works a little bit differently. And networking was always so simple and easy to understand anyway, at least for me. So recently, we've started to see this emergence of standard plugins where Docker plugs into the environments running in. And the 2 primary ones is there's something called the container networking model, which is invented by Docker Inc., all open source, and again is integrated in their stuff. And then there's another one called the container native interface that there's an organization called the Cloud Native Computing Foundation that's part of the Linux Foundation, and they have been pushing that as the container networking standard. And again, there are plugins in Azure for both of these, and actually pretty much for all the clouds and data centers have plugins for these 2 models. Container storage is another area that's started out a little crude. In a container, sometimes you want to actually reach out to a database or reach out to a file system that lives outside the container. So they have this concept of a volume mount, and that's been in Docker pretty much from the beginning. But if you want to run against the essential problem comes down to this. If you have a container and it's talking to a file system that's outside of the container, and the container guys, and comes back, how does it find the data that it was using before? Is the easiest way to say it. There's more stuff than that. But that's been pretty non-standard, how that works. And a bunch of vendors have been building solutions. And there's now an effort called the, I wrote cloud storage interface. You can see where my mind is. Container storage interface that's being developed, led by Mesosphere, Docker, and a few other people to standardize that. I mentioned package managers, and I mentioned that Docker is kind of a universal package manager. But Docker is the package manager, again, for putting their code into that one container. What if you have an application that consists of a front end and a back end and some sort of a middle tier, and maybe a load balancer, so you've got 5 or 6 different containers? Well, there have been several things, including a thing from Docker, again, called Docker Compose, that allow you to put containers together, but it's really still not designed as a package manager that works the way we think of a package manager works, where you can push a bunch of stuff into some place and then pull down and get all that stuff. So Mesosphere has a thing called DCOS Universe, which is a package manager for Mesos. And then there's an open source project called Helm that works against Kubernetes, which is again a package manager for Kubernetes. Another concept is the concept of a service broker. And the service broker, it's an old concept, but this particular one arose out of Cloud Foundry's service broker. And it's another aspect of portability, because oftentimes you may have your front end and you want to talk to a database, but now when you're running on a laptop, it's a different database than when you're running in the cloud. And maybe it's running in different clouds, so it's a different database. And maybe you want to run your own database, and maybe you want to use one of these managed database services. So with a service broker, when your front end wakes up, it basically says, hey, where's my database? And you get back a connection. And the service broker is responsible for finding that connection to that database. And if there isn't one, it might actually do something like spin up another container with a database in it, so that this will work. So it gives you additional abstraction. I should add, just last week, Microsoft, we announced that we bought a little open source company called Deus, and they wrote Helm and an early version of the service broker, and those projects are open source projects. They're actually now in the Kubernetes incubation part of the group, and that team is going to be joining Microsoft and continuing that open source work. So another emerging area is container security. Containers get criticized, or certainly early on got criticized on security on the basis of the fact that they have this great advantage, right? I just said they all share the kernel, and that makes them more efficient. But the more you share, the more likely is that if some sort of an exploit happens, it's going to move from container to container or process to process. And so what you can do with a lot of these things is solve the problem by, if you do have this concern, and at Microsoft or the other major cloud vendors where we have a lot of multi-tenancy, so we have what we call the Coke and Pepsi problem. So Coke and Pepsi both buy virtual machines, and they might end up on the same physical piece of hardware, and you don't want Coke and Pepsi to be able to steal each other's soft drink recipes. So that's a different problem than the friendly multi-tenancy problem, where the developer A writes an application at your company and developer B writes a different application. You both want them to run up on the same hardware, because presumably they're both employees of yours and not going to try and hack each other. Well, so in this sort of environment where you just cannot make any allowances for any sort of security problem, having that extra isolation is really important. There's lots of other reasons why you want to isolate. Kernels matter. A Red Hat kernel is different from a SUSE kernel, even if they're both built out of Linus's tree. And certainly a Windows kernel is different from a BSD kernel. So there's other reasons why you may not want to share kernels. And so if you want one of these reasons for not sharing kernels, one good thing you may want to do then is combine containers with virtual machines. In the early days when Docker first emerged, people were like, is this going to kill virtual machines? Containers are going to replace virtual machines. And the answer is no. There's lots of other reasons. There's this security isolation reason. There's also this compatibility reason why you may want to not share kernels. And so you can use the two together and get, mix and match and get the advantages that you might want. However, if you do it this way, you have now, remember I told you how Docker made things so much simpler than using virtual machines. Now you're using containers and virtual machines. So you've got all the complexity and more, and you've got all the combinations of the complexity. Maybe one place you're running a Docker container, it's running on a virtual machine on AWS, so you need an AMI. Another place you're running a Docker container and it's running on Azure, so you need VHD. And somewhere else you're using VMware. And so it becomes very complicated easily. It's not that complicated, but it's more complicated than it was before. So one of the things that we're starting to see is the ability to combine a hypervisor and a container without you knowing it, just natively. You get the normal Docker experience, but behind the scenes, the system does this. So there's a little startup in Beijing called Hyper. I put a link to their website that has this approach. Microsoft has also done this approach. We have this thing called Hyper-V isolation, which we invented originally for Windows containers, where, like I said, you just say Docker run, foo, and additional flag says, I want it to be isolated. And when you do that, we put a lightweight hypervisor around the container. It's one that's optimized to do nothing but run containers. And if you know anything about programming and optimization, it turns oftentimes if you have some simplifying assumption, you have opportunity to optimize. The general problem is always harder to optimize for than a specific problem. And so by knowing that the only thing we're ever going to run in that virtual machine is a container, we can provide all sorts of optimizations. So it's not as fast as a shared kernel container, but it gets a lot of the way there, and you have this other isolation ability. That was originally announced for Windows. Yesterday, I was at DockerCon, and I announced that we're bringing Hyper-V isolation for Linux containers running on Windows, which means that you can literally type Docker run busybox, which is a Linux image, on a Windows desktop, and it'll come down from the hub and run, and you go into that machine, and it's running a Linux kernel, a real Linux kernel. And by the way, it's a choice of your Linux kernel, because as I mentioned, kernels matter. So in this model, there's one extra complexity still, which is you say, here's the Docker container I want, and here's the version of the kernel I want to run it on. Another trend in this area is building small, optimized host operating systems that are intended, again, to just run a container. And there's a series of vendors that have done this. Docker had a thing called Moby Linux for a while. Yesterday, they announced something called Linux Kit, which is built with that Moby technology, but it has a lot of configurations of it. So it's basically kind of a build your own Linux with a bunch of security features optimized for running containers. The limit of this thing is a thing called a unikernel. In a unikernel, you statically analyze your application and all the dependencies from the beginning, and basically build exactly the code stack that you need for this thing, all the way from the top to the bottom. This is kind of like what I was saying earlier with the old days when you wrote the entire program and it owned the whole world. Now, it's going to be running inside some sort of a hardware abstraction, like a virtual machine, but even in theory, you could imagine it could analyze what drivers you needed on the hardware and construct something. So you get the exact minimal thing. And there's an argument to be made, a good argument, that this thing is going to be more secure because you get static analysis. You have reduced your surface area and all your dependencies to the minimal possible thing. And there's a lot of research in this area. The one downfall to all of these systems so far, and I know this from operational experience, is that it's great as long as everything works. But the moment something breaks, then you suddenly are wanted to, or what would Scott say, you want to shh into your box, and it turns out that there's no shh daemon in there, so you can't do it, or your debugger tools or whatever it is isn't in there. And so it's certainly a fixable problem, but that's, there's definitely a lot of work to be needed. Plus there's usually, can you use every programming language? Can you statically analyze JavaScript in Node and things like that and get the minimal dependencies or not? So but it's useful to my mind to think long term about how this trend of containerization and pulling in dependencies might end up. Another aspect of container security, and I think this is more important than the other one, is that people say, well, we've got these containers now, and everybody's writing containers like crazy. Well, now we have container sprawl. How do we find all these containers that we're using? How do we patch them? And I was thinking about this about 2 years ago because somebody was asking me about container sprawl. Oh man, container sprawl. What are we going to do with container sprawl? And I suddenly realized we've already got this problem. It's just that we didn't have a container before. We have tar zip files and MSIs and deb packages and RPMs and DLLs and XCs and every sort of other thing, and they're all over the place, and they're all different formats. And you got the sprawl. And there's, there are products that try and analyze that everything that's possible in the system and figure out what's going on and build the systems. But it's complicated because there's all these different interfaces. So Salman Hikes talks about Docker providing a narrow set of interfaces, like the narrow waist of the internet. The narrow waist of the internet, if you've never heard that term, is the idea that in the middle you have TCP/IP and a couple of other internet protocols. At the top you have all sorts of applications, browsers and CLIs and anything you can imagine. And at the bottom you have a whole bunch of different types of network hardware and networks. And the narrow waist of the internet is what really enables the internet to be successful, because everybody can operate on these very narrow set of interfaces and everything interops. And so Solomon says Docker is trying to provide that narrow waist of containerization. And this is so important to container security, because if you have a small set of things, you have a Docker file that says, these are the dependencies I expected when I created the thing. You have a Docker image, which sounds like a really complicated piece of technology until you realize all it is a tar zip file. So that means you can crack it open, look inside, and see all the files and scan them and find out what's in there. You have this registry or hub. Everything gets pushed up into the hub, and then it gets pulled down into the hub into production. On production, every machine that is doing that has a Docker engine. It's an agent. It's a piece of code that's sitting there. So that image doesn't get onto the box unless the agent talks to it. And then you have an orchestrator, which knows all where your agents is. Well, with this combination, suddenly you have enormous visibility that you probably never had before into what's actually going on in your data center. And you can apply policy to those points. So you can combine CVE data about, I should add one more thing. The Docker images also have a secure hash code so that you can determine provenance. You can tell that Docker image didn't change between when it started and where it ended up. So you can take a CVE database, you can scan all of the images that are available, figure out this one's got Heartbleed in it, and then you can match that up with that hash sum, and you have an incredibly simple way to find all the images that might have Heartbleed in your system. And then you can apply policy. You can say, you're not allowed to push, maybe you're not allowed to build a Docker file that contains Heartbleed. Maybe you're not allowed to push it. Maybe you're not allowed to pull it. Maybe you go out, may not be a good idea, and kill all the running containers in your data center that contain that bug until it gets fixed. So, and so much of security is much more about understanding what's going on and having visibility and being able to react than some sort of technical black magic that's going to suddenly secure everything. So I think this is a really important thing. And there's several companies and products that are building these container security scanners. Now this is a little futuristic. And before I start talking about enclaves, I want to, little aside, how many of you read Adrian Collier's The Morning Paper? Good. So this is, if you are at all interested in educating yourself as a computer scientist, I highly recommend you just subscribe to Adrian Collier's blog. He works in London. I think he works at a venture firm. I'm not sure exactly what he does. But he does the most amazing thing. Every day, he puts a review of a cutting edge, well, sometimes he goes back and reads some old one, computer science research paper. And it covers a lot of different topics. He covers machine learning, he covers programming language theory, he covers unikernels, he covers containers, distributed databases, and other things like that. And these are papers where I struggled to read the paper in a week. Somehow Adrian managed to read it, and you know how hard it is to then explain it, and then write a short blog post that explains it every day. And even the explanations, sometimes it can be a little hard to follow, especially if it's not your area. But if you read a bunch of them, it turns up, it builds up, and pretty soon you're like, oh yeah, he talked about consensus algorithms a couple months ago, and now I'm reading about etcd, and it has a consensus algorithm in it, and I'll go back and learn stuff like this. I don't know how he does it, but in any case, I bring it up here in the context of there's this upcoming container security technology, or security technology called enclaves. The processor manufacturers, and particularly Intel with SGX, have got new instructions that they're building. And basically an enclave takes a chunk of memory, encrypts it, and as the memory goes through the cache, there's a hardware unit that unencrypts the memory as it goes through the cache lines in the processor. And it also makes sure that only certain types of instructions will run in that enclave. And you can set it up. Here's a encrypted code package that is signed, and I'm only going to allow the keys to unsign that, to decrypt it inside that enclave. And so when you run in theory in this mode, it works now, but I'd say in theory, because I'll tell you in a second there's some disadvantages. You can put a program up, upload it into an enclave, it decrypts, and then everything from then on, in theory, is completely encrypted. That means that if somebody is gotten a hold of the kernel, gotten into the machine, they still can't see the memory inside that box. They still can't read the data or change the program. And that means not only is it hard for a hacker, but say that you are running on a hoster somewhere and you're in a position where you don't even trust the hoster who's going to be able to look at your code. So these enclaves, I think potentially at least, are a next step in this process. Now, as mentioned, there's some disadvantages. There's some performance overhead of doing this encryption and decryption and things like that. The amount of memory that you can put into those enclaves is limited. There's certain instructions that just don't operate. You can't actually make a system call from inside an enclave. And then you still have another system. This will be the part that'll be the hard thing. Is the real question is what are all your inputs and outputs? Did you somewhere along the line, unless you just don't care what's going on there, you're going to have to get your data out onto a website. You can still leak your SQL queries or your customer data by just handing it out as part of your program. But in any case, this is an interesting approach. So my summary here is that while the container revolution is changing everything, it's enormously important and driven by Docker and these orchestrators and things like that. Now, we're kind of only in the middle of it. And I see a lot of trends in hardware, combination of hypervisors and these shared kernel containers, advances in storage, networking, and other things like that are going to, and as well as higher level models, they're going to kind of bring this together. And in 5 years or less, we're going to stop talking about containers again. I won't come and give another talk about this. And we'll just be talking about applications. And these things will kind of blend into the background. Super critical, but how many people, And I'm going to say this, and of course, somebody will say, well, I just came from a TCP IP networking conference. But anyway, how many people have to think about that level of network protocol now? It's the back end of things. So that is the end of my presentation. I was at DockerCon yesterday. I haven't had time to digest everything that they said yesterday or today, but if there's any, that's maybe an area for questions. I went through that kind of quick. Is there any questions?
Hi, thank you. Is there any, you talked about security and isolation there. Is there any, I guess, future work with isolation with noisy neighbors, with Coke and Pepsi and, that sort of thing, where Coke is trying to denial of service on the same hypervisor platform?
Yeah, absolutely. There's a lot of, in that, when security, we include denial of service and noisy neighbor sorts of problems, because in the extreme, you can do that thing. So there's actually, for example, the processor manufacturers are making instructions where you can have, how you can pin a process to a core. You can also carve up the L1 and L2 cache to make sure that there's no cache contention. There's a couple of other papers that are there's a really interesting distributed data center paper where they statically analyze across the data center what all the programs are doing and figuring out, well, this program and this program are going to contend to on the L1 cache, and so we'll put them on separate physical machines. So there's and then in the software world, it kind of works up from there. But yeah, that's another area. We're definitely in the middle of that journey. Did I stun you all? Or are you just hungry and want to go to lunch? Well, looks like blood sugar wins.